Yes. Everybody learned it so long ago, Isabel. And that's the problem with the way we teach. No, I know. We teach you guys all this stuff when you're like 5, and then we expect you to remember it when you're 16. Good. Any number with only 2 factors. 1 and itself. Now, I find myself often right now, I need to remind you of what a factor is. What is a factor? It's a number usually that is doing what? Multiplying with another factor. Okay? So, just to remind you, 2 times 3 equals 6. Those are the factors. That is the product. Any things that are multiplying together are factors. They can be variables, they can be numbers, it doesn't matter. Everybody cool? Now, Sage has pointed out the second thing that I wanted to talk about, because the prime numbers, it is very useful for you if you memorize about the first 10 of them. So the first one is 2, then 3, then 5, then 7. What's the next one? Everybody says 9.
No, it's not.
It skips 9 and goes to 11. Then what? 13. Then what? 17. Then what? 19. 2, 3, 4, 5, 6, 7, 8. Then? Nope. 23. Then what? Nope. 25. Nope. 29. And that's more than enough to have memorized. Now, a couple of things here. Sage already mentioned one. He said 2 and 3 are weird because they are right beside each other on the number line. And so far as we know, they're the only ones. The other thing that's very special is number 2. What is special about 2? It's the only even prime number, which makes it really the most powerful prime number of all of them. It is very, very useful. Now, the reason I say to Sage's point about 2 and 3 being beside each other and being the only ones of which we know is because we are still calculating prime numbers. The largest prime number that we know of is something up in the billions, which is really crazy to think that a number can be that big and only have 2 factors, itself and 1. Yes?
What are prime numbers used for?
Prime numbers are mostly used in cryptography, writing codes. But they are also used in communication. The weird thing about prime numbers is there's no pattern to them. We don't know what the next one will be, except by guessing at it. The only thing we know is that it's going to be an odd number. Yeah. Everybody cool?
Like the numbers that add up to it, to count to it, is to not be a prime number, has to be a full number. Or not decimals,
No decimals. Everybody good? Okay. Now, 2 is very powerful. So what we're going to do now is we're going to do 2 factor trees. Then I'm going to show you how they work for us. So let's do these factor trees. Now, the thing about factor trees is everybody is going to do them differently. But you will always end up at the same answer if you did it right. Okay? So the first branch is always 2 branches. What 2 numbers could we put there? We could put 2 and 27. And that's perfectly acceptable. Right? Because 2 times 27 is 54. What are 2 other numbers we could put there? We can't put 54 and 1. We could put 3 and 18. Right, 3 and 18 would be perfect. What else could we put there? 9 and 6. Everybody cool? I could put all 3 of them and it wouldn't matter. It doesn't matter how you start. And here's why. Because you're going to keep going. And we are going to keep going until we have only prime numbers. So if you were drawing a branch that ends at a prime number, you can stop that branch. So I'm going to use Sage's example because 2 is a prime number. So that branch stops, and I like to circle it. And it was 2 times 27. Now, is 27 a prime number? No, so we break it down again. What's 27 going to be? 3 and 9. Either of those a prime number? 3. So I circle it, and that branch ends. 9, 3, and 3. Right? So the prime factors of 54 are 2 times 3 times 3 times 3. Agreed? Now, we're grown-ups, mathematically speaking. Would we ever write 3 times 3 times 3? What would we really write? 3 to the power of 3. 2 times 3 cubed. Agreed? All right. Now let's do 162. That's a bigger number. That's a bit of a pain. But we know it divides by something. What? Why do we know it divides by 2? Because it's an even number. So we can go 2, which will end right there, and 81. What's 81? Is it prime? No. 9. 9 and 9. Are either of them prime? Nope. So I keep going. 3, 3, there's primes. And 3, 3, there's primes. So that would be 2 times 3 times 3 times 3 times 3. Would we ever write that? What would we write? 2 times 3 to the 4th. Is everybody cool? Now, you'll notice I have made my factor trees vertically, yes? Some of you may have had teachers that taught you to go horizontally. Does it matter? No. Can you go in a circle? Can you go in a zigzag? I don't care. But notice that no matter how we did it, we ended up with the same answers. Everybody cool? We just keep going till we get to a prime number. Good? All right. Now, how are these things useful? Well, the first one is greatest common factor, which is GCF. That's what it's abbreviated to. That is the largest factor of your set of numbers. Now, you can find the greatest common factor of any set of numbers. We only have 2. The 2 numbers we are working with are 54 and 162. Agreed? All right. The greatest common factor can be found using these prime factors as follows. By writing only the common factors. So, 54 was 2 times 3 cubed. Agreed? And 162 was 2 times 3 to the 4th. Yes? So what are the greatest common factor of 54 and 162? So I had 2 times 3 cubed, 2 times 3 to the 4th. So, is 2 common to both of them? Okay. 2. Is 3 common to both of them? 3. How many 3s? This guy has 3. This guy has 4. So I cancel 1 out because there's only 3 that are common to both of them. 2 times 3 cubed is 54. So that's the greatest common factor. Is 54 a factor of 54? Yes, because 1 times 54. Is 54 a factor of 162? Yes, because 3 times 54 is 162. Is everybody good? Okay. That's the easy one. You just count everything that is the same. 3 3s, 4 3s. There's 1 3 that didn't make the cut. Everybody good? Yeah? We're going to practice it a lot. So if you're even just starting to approach good, you're okay. Is everybody good? Okay. The lowest common multiple. This one's a little bit harder. It's an LCM. And you already have used LCMs. This is how we do 1/10 plus 1/7. We need an LCD. That's what you're used to calling this. But LCM is what it really is. Okay? And you can find them. The LCM is the smallest number which has your whole set as a factor. Everybody with me? The LCM is the number that both 54 and 162 are factors. Everybody with me? All right. And again, we can use prime factors to help us, but this way's a little different. To do an LCM, you do that by counting all the factors, but only once, which means we skip repeating factors. And I'll show you what I mean right now. Remember, to do LCM, which I'm going to do in green, LCM, we had 2 times 3 cubed and 2 times 3 to the 4th. Is 2 common to both of them? So we're going to keep 2. Is 3 common to both of them? Yes, we're going to keep 3. And we have to count every 3 once and no repeats. So I got 3 3s here, right? Does this guy's 3s cover this guy's 3s? Yeah. So we don't need to count this guy's 3s twice. So that's out. I only need to count this guy's. So it's 3 to the 4th, which is 162, which again makes sense. 3 times 54 is 162. So 162 is a multiple of 54. Because if I multiply 54 by 3, I get 162. And it's a multiple of 162 because if I multiply 162 by 1, I get 162. Is everybody good? Now, we haven't really done anything new. We're going to practice this a little bit on the next page. And I probably won't get to its actual use until tomorrow. But I want you to be good at doing the factoring part because where we're going to go with it, you really need to know it. Everybody okay? All right. Nathan, you had your hand up. Because 54 doesn't multiply by anything to equal 2. You're going up. Now, that is a good question, though, because the words are weird, right? The lowest common multiple had to be at least the biggest number, 162. And the greatest common factor has to be at least the smallest number, 54.
The smallest number that it would equal to.
Yeah, that's factors. So let's turn the page over and let's try this out. We'll do the first one together and then I'll let you do the next 2. And then I'm going to make a small change at the third one. Okay? So let's start this. I need the GCF and the LCM. I'll do GCF in blue. Well, no, we won't do that. First thing we'll do, what do we need first? We need the factor trees. Now, there's lots of ways to get factor trees. I know of a couple of other ways. If you're unhappy making the trees, I can show you another way. But if you're happy making the trees, just make the tree. I don't like the tree, actually, Sage. I like another way. Do you want me to show you just because? This is the way I do these. Since I know I need prime numbers, I don't waste my time with anything but prime numbers. 36, I know, divides by 2, correct? So I'm going to do 2. 2 goes into 36 18 times, right? 18 is not a prime number, but it's even. So I'm going to divide that by 2 to get 9. 9, I know, divides by 3 to get 3. And now you will notice here on the outside, I have all my prime numbers. That's the way I like to do it. But when I show that first, kids are like, what are you doing? I don't... And then I show a factor, like, oh, I get that. So I don't care what way you use. Now, just to show you that it doesn't matter, 36. Let's go with 6 and 6, because that's what most of you would probably say. 2, 3, 2, 3. Circle, 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 circle. 2 times 2, 3 times 3. 2 times 2, 3 times 3. See, it works. You do what works for you. Okay? You got what?
Even if you use bigger numbers, it works out to be the same.
Yeah, because you just keep breaking those bigger numbers down with prime numbers. Now, once again, I can do 120 my way. It's even. 2, 60. 2, 30. 2, 15. 3, 5. Or I can make the tree. Most of you are probably going to go 12 and 10, I hope. 3 and 4, there's an even. 2 and 2. And 10 is 2 and 5. 2, 2, 2, 3, 5. 2, 2, 2, 3, 5. You do what works for you. Everybody cool? Now, how should I write this? Because we're grade 10 math students now. Would I write 2 times 2 times 3 times 3? What would I write? 2 squared. And how would I write this one?
2 times 3 times 5.
Everybody agree? Okay. Now, the GCF, just to remind you, we only count common. So, is there a 2 in both of them?
Yes.
Excellent. How many 2s? There's 2 2s there. This guy can cover those 2. So there's 2 squared. Is there a 3 in both of them? How many? 1. Is there a 5 in both of them? No. So we're done. 2 times 2, or 2 squared is what? 4 times 3 is 12. And we're done. Cool? LCM, I'll do that in green, in red. LCM, we count everything, but only once. So, is there a 2 in both of them? How many 2s must I count to cover all the 2s? 3. Because this guy's got 3. That covers this guy's. So he's out. Right? What about here? Is there a 3 in both of them? How many do I have to count to cover it? 2. This guy covers this guy. So he's out. And I count everything once. Do I have to count the 5? Yeah, because I count everything once. What's 2 cubed? 8 times what's 3 squared? 9 times 5 is 72 times 5, which is 360. Is everybody cool? Yeah? Okay, you do B and C, and then when you get to D, I want to add one number. No, not 12. 12's a bad one. I'm going to add 49. Okay? So what's going to be different on 3? How many factor trees are you going to need? 3. Do you change your rules? No. Yep. 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 Remember, factors have to be less than or equal to the smallest number, and multiples have to be greater than or equal to the biggest number. Nope, wouldn't matter. Everybody cool? Go. You can do factor trees however you want, but I'm going to give you a hint. Later on, this way, if you can get comfortable with it, you're going to find that to be the most helpful when we go a step further with this. If you can wrap your mind around doing this kind of, I call it the stairway method, but I don't know what it's really called. The trees will work, don't get me wrong. But you will find as you practice more and more that you will probably like this better, but that's up to you. That's exactly why I do it. This keeps them nice, keeps them all in one place. Then you can't, forget this two way up here in the middle of the tree where a branch just happened to end. But again, it doesn't matter. Do what works for you. But if you're going to make trees and the numbers start getting big, you got to pay really close attention to all the branches. Cool? Okay. I'm going to pause this, let you guys. Now, due to my own laziness, is everybody okay if I just use my stairs? Because that's what I'm most comfortable with. Okay. So 18, 2, 9, 3, 3. So 18 is 2 times 3 squared, right? 24. 2, 12, 2, 6, 2, 3. 24 is 2 cubed times 3. Then, GCF. Now, some of you, if you've been listening to me, I've given a shortcut to a few people. Notice in GCF, I had 2 cubed, 2 squared, 3 cubed, 3 squared, 3 to the 1. Notice in GCF, 2 was in both, and I used the smaller exponent. 3 was in both, and I used the smaller exponent. So, is 2 in both here? What's the smaller exponent? 1 or 3? 1, 2. Is 3 in both? What's the smaller exponent? 3 to the 1. So the GCF is 6. Now, obviously, the LCM is the opposite of that. So in LCM, you'll notice I used the biggest exponent of each. But there's one thing you have to remember. You count everything. So in this one, what's the biggest exponent? 2 cubed. Times what's the biggest exponent? 3 squared. Which is 8 times 9, which is 72. Is everybody good? Yeah? Okay. Now, hopefully you notice that if you get stuck ever having to do a fraction question, and you got to find a lowest common denominator, this is how you're going to, or a way you can do it much more easily. So 45 and 75, again, 45. It ends in 5, so what should I use? 5. That's going to get me 9. Then 9 is 3 and 3. So I've got 3 squared times 5. 75 ends in what? So I'm going to use 5 again, and that's going to get me 15. Ends in 5, I'm going to use 5 again. It's going to get me 3. 3 times 5 squared. My GCF, I do the pairs, everything that's common, and I use which? The smaller or the bigger exponent? Smaller. 3's in both, 3. 5's in both, 5. So my GCF is 15. My LCM, I count everything. And if there's pairs, I use the bigger exponent. What's the bigger exponent there? 3 squared times 5 squared, which is 9 times 25, which is 225. Yeah? What changes in D? I just got to do 3 groups. So 35 is 5 and 7. Okay, 5 times 7. 84 is 2, 42, 2, 21, 3, 7. 2 squared times 3 times 7. Why did I skip there and leave that space? There's no 5. That's just for my own organization so I can make my groups better. And lastly, I gave you 49. 7, 7. 7 squared. GCF is anything common to all 3. Is there one? Is 7 in all 3? How many 7s? 1. Done. LCM, I count everything. Do I count this 2 squared? Yep. Do I count this 3? Do I count this 5? And how many 7s do I count? 7 squared, which is 4 times 3 times 5 times 49, which is 4 times 3 is 12, times 5 is 60, 60 times 49 is 2,400, and then 360, 2760, right? Somebody did it with a calculator, is that right? Okay. Is everybody cool? Okay. Easy day to get us back into math, right? Nothing new, based on something you did a long time ago. When you turn the page over, again, I only want you to do this side. This first one, you're just going to be doing some bigger numbers. You only make one factor tree, just a factor tree for 600. You're doing no comparison. You're just practicing factoring. All right? Now, some of you may remember some of the tricks for division. We've already talked about a couple of them. If a number ends in 0, 2, 4, 6, or 8, what can I divide it by? 2. Right? Do you remember the trick to divide by 3? You add them up. If 321, for example, 3 plus 2 plus 1 equals 6. If 6 divides by 3, then 321 divides by 3. Right? Everybody remembers that one? Okay. There's one for to divide by 6. If 2 and 3 work, then you can divide by 6. If it ends in 0 or 5, what can I divide by? 5. And I didn't get taught any of these shortcuts, so I don't know them. I think there's one for 7. No. There isn't? Okay. There's one for 9. If the numbers add up to 9, you can divide by 9. I think. Yeah. But those are really helpful ones. Those will get you through. Now remember, if you do on your step somewhere, for example, if you had 642, 6 plus 4 plus 2 is 12, so it divides by 3. 642 divides by 2. You could put a 6 there, right? Which would get you 107, right? But remember, that's not a prime number. So when you continued with your steps, you would have to remember that that is 2 and 3. Then you could go back down to the steps. Everybody understand? You don't have to put prime numbers out there. But again, if you're going to, remember that you still got to break them down. Everybody cool? Sweet. Easy day. Like 10 questions. You're going to do great. The answers are at the bottom. They're all right. And I'm pretty sure, well, we're not doing the right side till tomorrow. Gouda? Tomorrow you'll get back your cumulative and we'll go over it. And then we're going to use what we did today to help us with tomorrow's work. Go. Nobody should be taking home homework. You got half an hour left. Yes.